Is the screen visible?
Yes, ma'am.
Okay. Why is this happening? I mean, why are people required to ask? Okay, so today we are going to start with Zener diodes. So Zener diodes are basically those diodes that can operate in the breakdown region. And from our previous classes, we already have some background about what happens when a PN junction is in the breakdown region. Okay. Yeah, I know that, but how do I change? Is there a setting? Should I turn it on? Let's see. Okay. So Zener diodes are basically those diodes that operate in the breakdown region. And what happens in the breakdown region? This we already know. If you recall the IV characteristics of the diode, then we see that in the breakdown region, the diode, when it is sufficiently reverse biased, that is, when I have applied large negative voltage across the diode, at that time, there is large current flowing in the reverse direction across the diode. So when this happens, I say that my diode is in the breakdown region. And during this time, the voltage across the diode remains pretty much constant at value equal to minus Vz, which is also known as the breakdown voltage of the diode. Breakdown voltage of the diode. So two things in the breakdown region. The first thing will be very large reverse current will flow, and secondly, when very large reverse current is flowing, the voltage across the diode will remain pretty much constant at the value equal to the breakdown voltage of the diode. So in this part, we have to actually analyze the circuits where we are using Zener diodes in place of the normal diodes. So before we start with the analysis, let us first briefly see how this breakdown happens. So the phenomena of breakdown that happens in the diode is basically because of two mechanisms. The first mechanism is the avalanche breakdown, and the second mechanism is the Zener breakdown. So in a particular diode, the breakdown could happen because of either of them, not because of both of them happening at the same time, because they happen in different type of diodes. This we are going to see in a while. So either your breakdown will be because of the avalanche effect, or it will be because of the Zener effect. So what happens in case of avalanche effect is that when you increase the reverse bias across the diode, then what happens? The velocity with which the minority carriers were crossing the PN junction and entering into the other area, like electrons, like holes from the N region cross the depletion region and enter into P. Likewise, the minority carriers in the P region, that is the electrons, they move to the depletion region and then cross the depletion region and move to the N. So here the minority carriers, the velocity with which these minority carriers are moving across the PN junction also increases. Why do people not join on time? This will be very disturbing. It's already 4:07. Okay, so what I was mentioning over here is that in the avalanche effect, when you increase the reverse bias voltage, the velocity with which the minority carriers are traveling across the PN junction, which actually contribute to the reverse saturation current, also increases. And once the velocity increases, the kinetic energy possessed by these minority carriers also increase. So we know that the kinetic energy is actually given by half mv square. So if the velocity is increasing, the kinetic energy is also increasing. So what happens is that in this case, the kinetic energy becomes sufficiently high so that when these minority carriers, they collide with the ions present in the p type or the n type region, they knock off the electrons which are present in the valence shell of this ion. So when they knock off the electrons or holes from here, so in turn you have new charge carriers which are being created. So what happened? You increase the reverse bias voltage. When you increase the reverse bias voltage, the velocity of the minority carriers that were causing the reverse saturation current also increases. When the velocity increases, the kinetic energy increases and it becomes sufficiently high such that when these minority carriers are colliding with an ion, they are capable of dislodging the electrons which are present in the outermost shell of that particular ion. So if this collision was not happening, then in that case the ion is otherwise an atomically stable structure. That means it was carrying some charge, but that ion was not contributing to the flow of current. लेकिन अभी collision की वजह से क्या होगा कि the energy of these minority charge carriers which are coming through the depletion region, this energy gets absorbed by the electrons in the outermost shell of that particular ion, thereby dislodging these particular electrons, and in turn you have more charge carriers being created, electrons also as well as holes also. And then the energy of these new electron holes which are created, this is also sufficiently high. So these will further go on colliding with other ions present in the p and n regions, thereby creating more and more charge carriers. So this cumulative effect is known as the avalanche effect, and the result of this effect is the flow of very large reverse current. So this is the first phenomena, avalanche effect, in which you are creating large current because of the presence of high velocity of the minority carriers. In the second type of breakdown effect, that is the Zener effect, what happens is when I increase the reverse bias voltage, then the electric field which is present across the PN junction increases, and when this reverse bias is a sufficiently high value, the electric field across the junction is also sufficiently high value. So this could be something on the order of like 2 raised to the power of 2 into 10 raised to the power of 7 volt per meter. So when the electric field reaches to this range, then in that case, what happens? This electric field exerts the force on the atoms so that इनके बीच में जो कोवेलेंट बॉन्ड होता है, it starts breaking. The covalent bond breaks, and out of these covalent bond, the electrons are pulled away. So these additional electrons which are being pulled away from the covalent bond, they contribute to the carrying of the extra current when we have the Zener breakdown. So the conclusion over here is, in both these effects, the avalanche effect as well as the Zener effect, the end result is same. That is, you are going to have very large reverse current, but the cause is different. In the first case, that is in the avalanche effect, the cause is the high velocity and the subsequent collisions of the minority carriers. And then in case of Zener effect, this is because of the presence of high electric field across the junction. So this is one main difference between the two. Other than this also, there are several differences. So I mentioned just in the previous slide that both of them are not going to happen together. So they do not happen together. Why? Because avalanche effect is mostly observed in the diodes where the PN junction is lightly doped. Whereas the Zener effect is observed in those diodes where the PN junction is heavily doped. This is another distinction. Then apart from this, in the experiments, it's observed that when the breakdown is happening because of the Zener effect, the IV curve that you see is more steep. So this will be like almost a steep curve in this way. Whereas in case of avalanche effect, the curve is not that steep. So it will be slightly like this. This voltage can be approximated as constant voltage, but this is not as steep as the curve which is observed in case of the Zener effect. So that's another distinction. One more distinction is that in case of Zener diode, the breakdown voltage VZ, this is observed around in the range of 6 to 8 volts. Whereas in case of avalanche effect, this breakdown voltage is slightly higher. It could be greater than 8 volts. Typically 8 to 10 volts से ज़्यादा ही होता है in case of avalanche effect. So that's another distinction. And then the last distinction is about the temperature coefficient. So in case of Zener diode, the temperature coefficient is negative. What do I mean by this? Temperature coefficient is negative means that if I increase the temperature across the PN junction, then my breakdown voltage is going to decrease. Whereas in case of avalanche effect, the temperature coefficient is positive, which means that if I increase the temperature, then the breakdown voltage is also going to increase. So this is a very brief discussion just to give you an idea of what happens when the breakdown occurs. So we already know that if the breakdown is happening, then large reverse current will flow and the voltage across the PN junction will remain constant. But the reason behind it could be different. It could be either because of the collisions of the minority carriers leading to a cumulative effect. That's what's the avalanche effect. Or it could be because of the presence of high electric field that breaks the covalent bonds, thereby pulling away the electrons, which we call the Zener effect. And then there are other distinctions. One happens for the lightly doped semiconductors, other happens for the heavily doped semiconductors. Then you have the distinction in terms of the breakdown voltage and the temperature coefficient. These are a few theoretical findings which is related to the breakdown of the PN junction diode. But when we use the Zener diode in the circuits, we are not going to bother whether the breakdown is happening because of the avalanche effect or it is happening because of the Zener effect. In fact, all the diodes which are designated to operate in the breakdown region, they are known as the Zener diodes, irrespective of ki breakdown kaise ho raha hai. So hereafter, when we are solving the circuits, we are not going to see if it's the avalanche effect or if it's the Zener effect. Okay? Any doubts?
And why is alpha positive for avalanche effect?
This is actually because of the fabrication properties. I cannot answer this right now because I need to refer to that. You will read about this once you take the courses on this device fabrication and materials. So as far as I know right now, this is because of the property of, doping and the way the PN junctions are being fabricated.
Okay, ma'am.
Okay. Okay, so now we will move to the actual thing where we are going to use the Zener diodes for the purpose of analysis in our circuits. So this is the symbol of the Zener diode. So it will be like a regular diode symbol, just that the vertical line you have some swing to the top and the bottom. So this swing denotes that the diode can also work in the breakdown region. So we have seen that the Zener diodes work in the breakdown region. That does not mean that it cannot work in the forward bias region or the reverse bias region. In fact, Zener diodes can work in all the three regions. It can work in the forward bias region also, it can work in the reverse bias region also, and it can work in the breakdown region also. But for forward biasing, Zener diodes are rarely used. Why they are rarely used? Because actually the fabrication of Zener diode is more complex compared to the ordinary diode. तो फॉरवर्ड बायस रिवर्स बायस के लिए तो ऑर्डिनरी डायोड भी यूज कर सकते हैं, तो व्हाई डू यू नीड अ स्पेशली फैब्रिकेटेड diode? So therefore the use of Zener diodes in the forward bias region is very rare. Mostly if it will work in the breakdown region. If it's not in the breakdown region, then it could be simply reverse biased. So what we are going to see now is when the diode is forward biased or reverse biased or in the breakdown region, how can we replace that in the circuit, and then how the circuit analysis can be done. So here in this figure, we have the typical IV characteristics of the Zener diode. Clearly we see that there are three regions: the forward bias region, the reverse bias region, and the breakdown region. तो फॉरवर्ड बायस रीजन में तो कोई चेंज नहीं है. यू विल हैव सम करंट व्हिच इज गोइंग टू have the value greater than 0. This is same as that of the ordinary diode. And in this region, we ignore the voltage drop. So the voltage drop across the diode, this will be equal to 0. So if anywhere you see Zener diode working in the forward bias region, we are simply going to replace that Zener diode with a short circuit, just the same way we were doing that for an ordinary diode. Now, if the Zener diode is working in the reverse bias region, then what we do is we ignore the current flowing through the Zener diode and say that there is some negative voltage drop across the Zener diode. So that means if it's in the reverse bias case, I'm going to replace this with an open circuit. This also I know, this is same as the ordinary diode. But what happens in case of breakdown region? In breakdown region, I know that there will be a large reverse current. So in this case, I denote the current I as a value which is less than 0. So less than 0, that means it will be a negative value, and this negative is actually denoting that this is a reverse current and not the forward current. Therefore, I'll say that I is less than 0. And what about the voltage across the diode? In this condition, this will be equal to the breakdown voltage of the diode, that's Vz. So that means if in a circuit, I see a Zener diode which is operating in the breakdown region, I'm going to replace that Zener diode with a DC voltage whose value is equal to Vz. That's the only difference. This we have already seen, this we have already seen, but this is what we need to see now through the help of examples. So if the diode is in the breakdown region, I'm simply going to substitute that diode with a DC voltage whose value is given by the breakdown voltage of that diode. So here is the representation. So here you have the Zener diode, and here you have the equivalent DC voltage with which I'll replace the Zener diode. So here I want you to observe the polarity. So in the diode, we say that this terminal is positive and this terminal is negative. And generally, इसके cross जब voltage mark करते हैं, then we say that this is plus minus V. That's how we have been doing in the previous classes. But here, because we know that the Zener diode is working in the reverse bias region, of course, so voltage Vz is going to be a negative voltage. Therefore, how do I connect the battery? I connect the battery such that the negative of the battery is towards the positive of the Zener diode, and the positive of the battery is towards the negative of the Zener diode. तो इससे क्या होगा कि whenever I am using this value Vz in the circuit, मुझे Vz को minus नहीं लिखना पड़ेगा, because already I have taken care of this in the polarity while I am drawing the diagram. So this we are going to see as we solve the circuits. This is one thing that we need to remember is how should I place this DC voltage so that the polarity is correct. This is the case for an ideal model. If the diode is not ideal, then in that case, the better approximation could be a DC voltage placed in series with a resistance RZ. So this voltage is there, plus you have some additional voltage which will happen across this RZ, and this is going to better approximate the Zener diode when we do not consider this as an ideal diode. But this case we are not going to discuss over here. For the sake of simplicity, we will limit our discussions only where we replace the diode by simply a DC voltage source. Okay, so with these concepts, now we are going to see what type of questions we can have in case of Zener diodes. So there are two basic applications of the Zener diode. The first application is, of course, the very important application. This is the application of voltage regulator. And the second application is that it could also be used for the purpose of clipping. So clipping, last time भी हमने देखा था by using ordinary diodes. This can also be done by using Zener diode. So in this case, this is more appropriately referred to as AC voltage regulator, because you will give some sinusoidal input and then in the output you will see that some portion of the diode has been clipped off. So actually it is clipping, but what's happening is that it is regulating the output voltage so that output does not exceed beyond a given threshold. So this, the first application, voltage regulator, this you can think of as a DC voltage regulator. And the second application, which we are calling as clipping, this could be an AC voltage regulator. So for a typical voltage regulator circuit, I mean the very basic diagram that goes is in this way. So you will have some input voltage. Here I am taking a DC voltage. Let me call this as plus minus VI. And then this is some resistance R. And in the parallel branch, I have placed my Zener diode, which is having the breakdown voltage of Vz. So see the polarity that I have marked over here. The positive I am marking towards the negative of this diode. This does not mean that this terminal is negative. Diode का ये terminal तो positive ही है, but I am marking this in the opposite way so that I don't have to write minus while I am solving the circuits. And then other than this, I have a load resistance RL. Across the load resistance RL, let us have voltage drop VL, and the current which flows in over here, let us say this is denoted by IL, and the current which flows over here, this will be denoted as IZ. इसके across voltage drop को VR कह देते हैं, and the current through this is IR. So this is your simple and most basic form of voltage regulator circuit using a Zener diode. So how will the question be formulated? So in these type of circuits, ऐसा कोई circuit दिया होगा and it would be required to find out say VL or VR or IZ or the power which is dissipated across this Zener diode. This will be equal to VZ into IZ. Or you could be required to find the range of load resistance RL for which the voltage is regulated at the output, or one more variety could be the range of input voltage VI for which the voltage across RL is regulated. So whenever I say that the voltage across RL should be regulated, that means the voltage appearing across the load resistance should be constant, and this constant value should be equal to Vz. This is what I mean when I say that voltage regulation is happening. Okay, so next we are going to see three cases in which we will try to compute all these factors based on how the diode is connected, what is the value of load resistance and what is the value of input resistance. So these this further analysis I have, for the sake of simplicity of your understanding, we will see this under three categories. So this is the first category. In this category, you will have VI as fixed. You will also have the value of load resistance as fixed. And just mark that in this question, it is nowhere mentioned that the diode is operating in breakdown. ऐसा क्वेश्चन में नहीं दिया हुआ है. So if you read the question just says that for the Zener diode network, which is shown in this figure, we need to determine these parameters and then we need to repeat this when RL is 3 kilo ohms. So this is the first case where VI is fixed. The value is given as 16 volts. RL is also fixed, which is given as 1.2K. And it's not mentioned if the diode is in breakdown or it's in reverse bias or whatever. So the first step that you should do in these type of questions is to identify if the diode is on. What do I mean by this? Zener diode is on का मतलब है if it is operating in the breakdown region or not. We are not talking about the forward bias case at all. I want you to forget that it can operate as forward bias. Only in special cases which are very rare that happens. So if in the question it's written that find the value of XYZ such that Zener diode is on, that means you need to consider that the Zener diode must operate in the breakdown region. अब ये आइडेंटिफाई करना है कि जीनर डायोड जो यहाँ लगा हुआ है ये ब्रेकडाउन में है कि नहीं है. सो फॉर दैट व्हाट वी आर गोइंग टू डू इज the breakdown voltage is given to us. This is given as 10 volts. So what we do is we remove this diode. इसको उठा के अलग रख लेते हैं and then we'll see what is the voltage which is appearing across these open circuit terminals. So then your resultant circuit is going to look like this. ये हम Zener diode थोड़ी देर के लिए निकाल के रख देते हैं and we'll say that the voltage over here is V. And then you have the load resistance RL. This is R and this is input voltage. So in this situation, what is the value of V which is appearing over here? So this V will be same as the voltage drop that is appearing across the load resistance because this is coming exactly in parallel to the load resistance. And if I want to find out the voltage drop across the load resistance, this is an easy thing because it's a simple series circuit. So I'll say that the voltage across the load resistance, this is also equal to V. In my case, this will be equal to RL divided by RL plus R multiplied by VI. And all the values are given. What is RL? RL is 1.2K divided by 1.2K plus 1K multiplied by 10. So if you calculate this, how much this comes out to be? This will come out to be something around 8.73 volts. So that means in this circuit, the voltage which is appearing across these terminals is how much? This is equal to 8.73 volts. लेकिन ब्रेकडाउन में जाने के लिए कितना वोल्टेज चाहिए? ब्रेकडाउन में जाने के लिए जितना वोल्टेज चाहिए, that's equal to 10 volts. So this means that in the first case, when RL is given by 1.2 kilo ohms, the diode is not operating in the breakdown region. So if the diode is not operating in the breakdown region, then it's in the reverse bias region. And how do I proceed with the analysis? If the diode is in the reverse bias region, I simply replace the diode by an open circuit, जैसे कि यहाँ पे किया हुआ है. So now to find out these parameters, I'm going to consider this circuit. So in this circuit, the first thing that I want to find is VL. What is VL? VL is the voltage drop across this resistance. And this, I just found out, this was equal to how much? 8.73 volts. Then the next thing is VR. So again, this is a simple series circuit. VR, you can find by voltage division or you can also find simply by subtracting the value of VL from the input voltage. So VR will be equal to VI minus of VL. That's 16 minus, this is 8.73. This is going to be how much? 7.27 volts. Then how about IZ? Because the diode is working in the reverse bias region and we ignore the current flowing through the diode in the reverse bias region if the diode is ideal. So I'll say that Iz is simply equal to 0. And if Iz is equal to 0, Pz will be equal to Vz into Iz. So this is equal to again 0 because Iz is equal to 0. Okay? Any doubt in this?
No, ma'am.
Okay, so if there's no doubt, we'll do the next part of this. Next part में क्या करना है? We have to replace the value of this load resistance from 1.2K to 3K. तो अब जब यहाँ पे 3K कर दिया तो क्या होगा? Let us see how much value of V I get. So if RL is equal to 3 kilo ohms, then what will be V? This will be equal to VL. Again, the same formula, that's RL divided by RL plus R into VI. So all the values I know. RL now is 3, VI is 16. अच्छा यहाँ पे VI was 16. Divided by, this is 3 and R is 1. This is 3K, this is also 3K, this is 1K. So if you solve this, how much it will be? 16 divided by 4 is 4, 4 3s are 12. So when I replace the load voltage by load voltage having the value of 3 kilo ohms, the voltage which appears across these open circuit terminals is how much? It's 12 volts. But I know that in order to keep this diode into the breakdown region, I need the voltage at least equal to 10 volts. That means for case B, the diode is for sure working in the breakdown region. अब अगर diode breakdown region में work कर रहा है तो what I do? I am going to replace this diode with a battery such that the positive of the battery will be towards the negative of this diode and the negative of the battery will be towards the positive of this diode. So let me redraw the circuit over here. This is going to look like this. This is my plus minus VI and here I have R. Here I will have a DC voltage source plus minus whose value will be equal to the breakdown voltage of the diode, that is Vz. And then I have my load resistance over here, RL, through which the current IL will flow. So अब इसमें first thing that I need to find out is VL. So before drawing this circuit, I saw that VL was equal to 12 volts. But actually in this case, VL is not equal to 12 volts. Why? Because when VL is equal to 12 volts, I know that my Zener diode went into the breakdown region. And when it goes into the breakdown region, the voltage across this will be maintained constant equal to Vz. And since RL is placed in parallel with Vz, the voltage drop across this load resistance will also be equal to Vz, and this will be equal to how much? 10 volts. Yeah, Vz is 10 volts. So now the value of VL will be equal to 10 volts. That means by pushing this diode into the breakdown region, I have regulated the voltage across this load resistance to 10 volts, which would otherwise be 12 volts. So that's the first part. What about the remaining parts? Remaining parts are easy. This you already know, VR will be equal to VI minus VL. VL in this case is 10. So this will be equal to 16 minus 10 is equal to 6 volts. Then third thing that I need to find out is IZ. So IZ is the current in this branch and IR is the current over here. So I can apply KCL over here if I want to find out IZ. So I'll say that IR is getting divided between the branch containing the Zener diode and the branch containing the load resistance. So IZ will be equal to IR minus IL. And IL I can calculate because I know VL, I also know RL. So this will be 10 volts divided by RL was 3 kilo ohms in this case. So this comes out to be 3.3 milliamperes. Similarly, you can find out IR also. What will be IR? This will be VI minus VZ divided by R. So this is 16 minus 10 divided by R was how much? 1 kilo ohms. So this comes out to be 6 milliamperes. So if you substitute this back over here, this will be 6 milliamperes minus 3.3 milliamperes. So your IZ will come out to be 2.67 milliamperes. That's the third part. And what about the fourth part? इसमें PZ निकालना था हमको. So PZ will be equal to VZ into IZ. VZ is fixed. This is 10 volts. And IZ I just found out. This is 2.67 milliamperes. So this will come out to be 26.7 milliwatts. So we just saw that by changing the value of this RL, this diode could either work in the reverse bias case or in the breakdown case. If it's in the breakdown, then we need to do the analysis differently. If it's in the reverse bias region, then the analysis would be different. Okay, any doubt? No doubt? Okay. So if there's no doubt, then we proceed with the second case. In the second case, you will have the value of VI as fixed, but the value of resistance RL will be variable. So this will be variable. Correspondingly, IL will also be variable. So the question may ask you to find out the range of this resistance RL or the range of this current flowing into the resistance RL for which the voltage is regulated. This would be the typical question. So like the question statement over here, it reads that for the network shown over here, we need to determine the range of RL and IL that will result in VRL to be maintained at 10 volts. इसके लिए other words that could be used is that voltage should be regulated और ऐसे भी कह सकते हैं कि Zener diode has to be on. So what to do? We need to find out the value or range of RL. That means एक RL min चाहिए और एक RL max चाहिए. इसके corresponding you will have IL max and इसके corresponding you will have IL min. So how do I do? I know that if I have to maintain this 10 volts across this load resistance, ये diode को on होना चाहिए. So although here it's not mentioned anywhere कि breakdown है, but we know that if I want to maintain the constant voltage, the diode should be in the breakdown region. And if the diode is in the breakdown region, the voltage drop across this load resistance will be equal to the breakdown voltage of the diode. And this is the property that we are going to make use of for calculating the value of R min. So what happens over here, if I write the expression for VL, this will be equal to, again, RL divided by RL plus R multiplied by VI, and this I'm going to equate to VZ, where VZ is known, VI is also known, R is also known. Only unknown factor is RL. So if you rearrange this a bit, you will get the value of RL min, and the RL min expression will look like R into VZ divided by VI minus VZ. I'm simply rearranging this expression. So for all the values of load resistance RL which are greater than RL min, we are going to have a regulated voltage at the output, that is VL will be equal to VZ. So can I calculate RL min? This will be equal to R की value दी है 1K multiplied by VZ is given as 10 volts divided by VI is 50 minus VZ is 10. So if you calculate this, this comes out to be 250 ohms. So RL min is 250 ohms. Corresponding to RL min, I can find out IL max. So this will be equal to VL divided by RL. That actually is VZ divided by RL min. VZ is given as 10. RL min you found out just now as 250. So this comes out to be 0.04 or 40 milliamperes. So these are my lower values. How about the upper values? Now I have to find out RL max. So RL agar max hoga, this means that IL will be IL min. This current will be IL min. So if minimum current is going in this branch, that means maximum current is going in this branch. And the value of this maximum current is given. This is usually the characteristic of the diode itself. And this is given in the specification sheet of the diode. So generally you will have the minimum current that this Zener diode can support and the maximum current that this Zener diode can support. ये दोनों figures specification sheet में मिल जाते हैं. So IZ max is what I already know. So IR is equal to IZ plus IL. This I know. But if I say that my IL has to be IL min, that means my IZ will be IZ max. And this will be equal to IR. I can calculate IR now. IR निकाल सकते हैं. This is simple. VI minus VZ by R. So how much this will be? VI is 50. VZ is 10 divided by R is 1K. So I have IR equal to 40 milliamperes. And IZ max, this is already given to us in the question. This is equal to 32 milliamperes. So in that case, IL min will be equal to 40 milliamperes minus 32 milliamperes is equal to 8 milliamperes. So now I have IL min. And if I have IL min, I can find out RL max from here. This will be equal to VZ divided by IL min. VZ is known. This is 10. IL min we just found out. This is 8 milliamperes. This is going to give me something like 1.25 kilo ohms. So the range of RL for which the output voltage is regulated is that RL should be greater than or equal to 250 ohms and it should be less than equal to 1.25 kilo ohms. Similarly, the range of current, load current IL, this is greater than, what is the minimum value? 8 and the maximum value is 40. This has to be greater than 8 milliamperes and it has to be less than 40 milliamperes. This is my required range. Then the next part of the question says that determine the maximum wattage rating of the diode. Maximum wattage rating, that means I need to find out PZ max. So PZ max will be equal to VZ, ये तो fix रहेगा, multiplied by IZ max. And IZ max is already given in the question. So this will be 10 multiplied by 32 milliamperes. So this comes out to be 320 milliwatts. Is this fine? So here VI was fixed. RL could be varied. So we learned how to find out the values of RL such that the output voltage is regulated. Any doubt in this case? Okay. So then we move to the third and the last case. Here RL value will be fixed and VI has to be variable. So the question will say that you need to find the range of values of VI for which constant voltage is maintained at the output. That means you need to find out VI min and you need to find out VI max. तो VI min निकालने के लिए क्या करें? We are going to reuse the same condition that I have to increase VI so much such that ये जो डायोड है ये ऑन हो जाए, और जब ये डायोड ऑन हो जाएगा then the voltage across this load resistance will be equal to the breakdown voltage of the diode. So VL, which is actually equal to VZ, this will be given by my expression RL divided by RL plus R multiplied by VN. So now here VZ is known, RL is also known, and R is also known. So only unknown thing is VI. So if I rearrange this equation, the expression for VI min would be RL plus R multiplied by VZ divided by R. So all the values are known over here. If I substitute, VZ in this case is 20, RL is 1.2K, R is 220 divided by, again, this is RL. This will be equal to 1.2K. So if you calculate, this is going to come out to be 23.67 volts. This is my minimum value of the input voltage. अब maximum value निकालने के लिए क्या करें? VI max. So if you see, if I apply KVL over here, then my VI will be equal to IR into R plus VZ. यहाँ पे वेरिएबल क्या है? VZ तो फिक्स्ड है, R भी फिक्स्ड है. The only thing that could vary is IR. So that means if IR is actually IR max, then correspondingly the value of input voltage that I will get will be VI max. So VI max is equal to IR max multiplied by R plus VZ. So now the question is, how do I calculate this IR max? So again, if I apply KCL, I know that IR is equal to IZ plus IL. Now in this case, IL is fixed. Why IL is fixed? क्योंकि RL तो fixed है और voltage भी fixed है, क्योंकि मुझे पता है कि डायोड ब्रेकडाउन रीजन में ऑपरेट कर रही है, तो वोल्टेज इसके अक्रॉस फिक्स्ड ही रहेगा. So IL is fixed. Only thing that can vary is IZ. So this will be equal to, if I want to find out the maximum value of IR, this will be equal to IZ max plus IL. And IZ max is again given in the question. This is the specification of the diode itself. This is 60 milliamperes. तो मुझे निकालना क्या है? बस मुझे निकालना है IL. And this will be equal to VL by RL. VL मेरा है 20 और RL है 1.2K. So this 20 divided by 1.2K is going to give you 16.67 milliamperes. And if you add this to 60 milliamperes, you will get the value of IR max as 60 milli plus 16.67 milli, that's equal to 76.67 milliamperes. So this is how I have IR max. Now I get back to this equation over here. I know everything. I know IR max. I also know R. I also know VZ. So if you substitute everything over here and find out the answer, this should come out to be 36.87 volts. Just do this after the class and verify if these values are correct. So for a given load resistance RL, we determined the values of input voltage such that the output is regulated. In the first case, to find the minimum value, we use this conventional expression जो पिछले दो slides में use कर रहे थे, and for finding out the maximum value, we just applied KVL over here and said that if this current is maximum, this input voltage also has to be maximum. So these are the three basic varieties under which you can find the questions. It could be mix and match of these conditions. एक एग्जाम्पल है जो कि बुक में दिया हुआ है. आई वॉन्ट यू टू डू दैट एग्जाम्पल एंड सी. सो इट्स अ सॉल्व्ड एग्जाम्पल. सो इन दैट केस व्हाट हैपेंस इज you are given both the values of IZ max as well as IZ min. And then it is required to find out the range of RL for which the diode operates in the breakdown region and the range of input voltage for which the diode operates in the breakdown region. So this example is even simpler. इसमें करना क्या पड़ेगा? First you need to do is you need to write down the expression for IZ in terms of RL. So in the first case where you have to find out the range of RL, वहां पे input voltage दिया होगा. So you write the expression for IZ and this expression would be simply IR minus IL. So you write down the expression for IR, this will be VI minus VZ by R and this IL would be VZ minus RL. तो ऐसे एक expression आएगा current का through the Zener diode and this expression of current which is in terms of RL, this you have to place in between these two inequalities. That means this IZ min say greater than equal to बड़ा होना चाहिए ये expression and should be less than equal to IZ max. So by taking this condition, you will get the value of RL max and by taking this condition, you will get the value of RL min. Similarly, when you will solve for the range of VI, in that case, you will have the expression of IZ in terms of input voltage VI because this will not be given and RL will be given. So again, you need to do the same thing. IZ का expression लिख के place it in between IZ min and IZ max and correspondingly find out VI min and VI max. So I'm not taking this example in the class because this is solved example. And if you have understood the concepts that we have discussed, how to approach these type of questions, that is pretty simple. Any doubts?
No,
Ma'am, how is VL equal to RL into VI by RL plus R? For that, IR should be equal to IL, right? The current should be same.
कहाँ पे?
How is VL equal to RL into VI by RL plus R? That first equation.
This one?
Yes, ma'am.
This is simply by rearranging. So what I did is I wrote the expression for voltage drop across this resistance. This is a simple series circuit. So this will come by voltage division rule. So this is RL divided by RL plus R into VI. And I know that
But
if the diode is
currents are
on,
different, right? The currents are different through R and through RL.
the currents are different through RL. हाँ, तो currents तो different होंगे, but I'm equating the voltages. Because this is in parallel with this, the voltage will be same, right? तो ये जो expression मैंने लिखा है voltage का, I will equate this to VZ.
Okay.
ठीक है? Do this for yourself once. एक बार खुद करके देखो, value substitute करके देखो. If still there is doubt, then you can ask me in the next class. So with this, I think we have pretty much covered the regulator part of it. Next class में एक AC regulation वाला example देखेंगे. And if time permits, then we'll start with the transistors. Okay, so if there are no more doubts, then thank you so much.